Hi everybody. So in this video, we're going to look at how we can model real-life situations using differentiation. So we're told that an open top cylinder has a total external surface area of 192 pi centimeters squared. And if r is the base of a radius and h is the height, and then to find an expression for h in terms of r. So if we create the net of this open cylinder, this rectangle would be the curved surface area and this circle would be the base of a cylinder. We know this length would be the circumference of the circle, so 2 pi r, and this would be the height of the cylinder, so h, and that the base would have a radius of r. We can work out the area of this rectangle as 2 pi rh, and the area of a circle as pi r squared. So the total area of this cylinder would be 2 pi rh plus the pi r squared. So we can say 192 pi is equal to the rectangle area plus the circle. And to find an expression for h in terms of r, well, we can divide through by pi, and then move this r squared to the left-hand side, and divide both sides by 2r. So the height will be 192 minus r squared over 2r. So for part B, hence show that the volume can be written as this. So we know the volume of a cylinder is the area of a base multiplied by the height. So V will equal pi r squared h. Then all we need to do is substitute this expression for h into here. So at this point, we can cancel this r with one of the r's here, and then we can bring this 2 out in front of our bracket. And then we'll just expand out this r. And this is what we were asked to show here. Okay? For part B, use this to find the maximum possible volume of a cylinder and verify that this is the maximum value. So we know that the maximum volume is when dV by dr will equal 0. So what we need to do is we need to differentiate this equation for V with respect to r. And this will be pi over 2 lots of 192 minus 3r squared. And we know that this is equal to 0 for a maximum volume. So we just need to solve this equation. We can move the pi over 2 to the left-hand side, and that will become 0. And then we can move the negative 3r squared to this left-hand side. So we'll get 3r squared is equal to 192. So therefore, we'll divide both sides by 3 and take the square root, so r will equal 8. So now we can work out the maximum volume by substituting this value of r into our equation here. We can work this out on a calculator and we get 512 pi centimeters cubed. Okay? Then we can verify that this is a maximum value by finding the second derivative of the volume. Because we know that when d squared v over dr squared is less than 0, this will be a maximum turning point. So if we differentiate again dv by dr with respect to r, we'll get pi over 2, this constant will go, and this will become negative 6r. We can simplify this, and we get negative 3 pi r. Then we'll substitute the radius as 8 into here, and this will give us negative 24 pi, which is less than 0. Therefore, when the volume is 512 pi centimeters cubed, this is a maximum volume. Okay? Let's try one more question. So in this question, we're told that a closed carton is in the shape of a cuboid, and the base is a square of side x. The total surface area is 486 centimeters squared. We've been asked to work out an expression for the volume of a carton in terms of x, and then to find the maximum possible volume, and justify that this is the maximum. So perhaps you want to try this question yourself. You can pause the video, and when you come back, we'll go through the work solution. Okay, so welcome back if you had a go. So we're given that this length is x and this length is x. What we don't know is this length. So I'll call this L. So now the surface area of this cuboid will be the area of this face, which is Lx, plus the area of this face, x squared, plus the area of this face, which is again Lx. But we have to double these three because we've got the other three sides. So 486 will equal 2 lots of 2Lx plus x squared. And then we can divide both sides by 2, and this will give us, and we need to make L the subject of this because we want the expression for a volume only in terms of x. So to make L the subject, we'll move this x squared to the left-hand side and divide both sides by x. So then to work out the volume, we'll multiply the area of this face by L in terms of x. We can simplify this because this x will cancel with one of these, so we'll get, and then we can expand out this bracket, so v will equal 243x minus x cubed centimeters cubed. So for part C, find the maximum possible volume, justifying that the value found is a maximum. So if it's a maximum, then we'll have a stationary point and dv by dx will equal 0. So we need to differentiate this with respect to x. So this will become 243 minus the 3x squared. And then we can set dv by dx equal to 0 and move this negative 3x squared to the left-hand side. We'll divide both sides by 3. So x squared will equal 81. So x will equal 9. And then we'll substitute this length into the equation for a volume. And this will give us a maximum volume of 1,458 centimeters cubed. Then finally, we can justify this as a maximum by differentiating dv by dx. So d squared v over dx squared, if it is a maximum, should be less than 0. And when we differentiate this constant will go, and this will become negative 6x. We'll substitute in x equals 9, and we get negative 54, which is less than 0. D squared v over dx squared is less than 0, therefore 1,458 centimeters cubed is a maximum volume. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe. And you can download the full lesson and worksheet from my website, mrmathematics.com. I'll leave a link in the description below. Thanks again and take care.